All right. Thank you so much, everyone. We have 45 attendees today. Thank you so much. Thank you for joining us today. Good morning, good day, wherever you are in the world. Okay. Hope you had a good day. Together with me right now is Dr. Vino Mada. He will be our presenter. Okay. So yeah, just a few reminders before we start. Okay, so just make sure all the notifications from your end will be disabled so that you'll be able to focus on our presentation today. We have a very good topic that will be discussed by Dr. Vinu. So we just want to make sure that you'll be focused on that one. Okay. So follow the instructions on your screen. Okay. All right. So, yep, again, welcome everyone. My name is Marvin, Marvin Yu. I'm one of the course advisors here at EIT, and together with me is Dr. Vino Madha. He's actually one of our EIT lecturers, and he will be introducing himself to you guys after this. Okay, so today's topic would be recent trends and application of heat and mass transfer. So, this will be a technical topic that will be delivered again by Dr. Vino Madha. Okay,
Thank you, Marvin,
all right.
for that. Yeah, you can
Okay.
go ahead
Yep.
and share
Yep.
few information. Then I can start. Yeah.
Sure, Doc. So, yep, let me just for common questions, of course, we encounter a lot of this. So someone will be asking if I'll be receiving the slides or video. Yes. Once you registered, in the next 2 business days, you'll be able to receive the copy of slides and videos, recordings of this particular webinar. And at the same time, since this is a technical topic webinar, we'll be providing a free digital certificate of attendance for those live attendees. So make sure to stay until the end of the session because the instructions will be provided to you afterwards. All right. Okay, now, so let me share with you about EIT. So, EIT is actually an education provider based in Perth, Western Australia. We also have a campus in Melbourne, and we just recently opened our campus in Brisbane. Okay, so we are actually dedicated to ensure that the students receive a world-class education and at the same time gain skills that can be implemented immediately on the workflows. Okay, or can be valued really with the employers. Okay, so which is really needed in the industry. Okay, so we call ourselves as engineering specialists because we're only one of the institutions that specializes in engineering. Okay, we deliver a wide range of programs like professional certificates, advanced diplomas, graduate certificates and diplomas. um, we also have the bachelor's, master's, and doctor of engineering, and these particular programs are industry oriented. All right, so we these are being designed by the industry experts to ensure that our students have the cutting edge skills, okay, which are valued by employers, and at the same time it remains current with the rapidly changing technology. As we all know, it's in engineering is a very fast industry. All right, so our programs, our vocational programs and higher education programs are actually having a world-class accredited with accreditation with the Australian government, and at the same time also recognized by under the three international engineering accords. So these programs are being delivered by our highly experienced engineers, subject specialists with applied knowledge, and then this is being delivered in a unique delivery methodology which makes use of live interactive webinars. At the same time, we have a global pool of experts, and at the same time, we have dedicated learning support officers and state of the art hands on workshops, remote laboratories, and simulation softwares. So that's basically EIT. And to know more about us, you can visit on our website or contact us course advisor so that we can actually explain to you further what EIT is and how we can actually help you with your educational journey. Okay. Okay. So yep, I will. Okay, so basically these are the agendas for today, which will be explained to you by Dr. Vinu. However, at the end of the presentation, there will be a short Q&A wherein all your answers will be, all your questions will be answered by me and Dr. Vino. So you can just post your questions in the chat and we'll be answering them for you later on after the presentation. Okay. So now, without further ado, let me forward the floor. Let me just give the floor to Dr. Vino. Okay, Doc, the
Thank
floor
you,
is
thank
yours.
you, thank you, Marvin, for that nice introduction to EIT. Let me just briefly tell me about myself. I'm Dr. Vinu Madhav. I'm currently based out of India, and I'm a mechanical engineer. I did my master's and PhD from Indian Institute of Technology. Then I have got more than 16 years of industry experience. So industry experience is very essential for all the faculties at EIT because we provide the industry touch to the theory. So I won't be discussing too much on the theory aspects. So in this webinar, I will be touching more on the practical aspects and applications of those theory, and that is what we try to provide uh, at EIT. And I've got a lot of research interests. So I've worked in automotive industry, I worked in steel industry, I worked in energy sector. And I teach units or courses at all the levels, at bachelor's, master's, as well as I supervise thesis students as well. That's about me. Now, let me just briefly go through the agenda and let me welcome you to this webinar formally from across the world. All participants are, I can see that you are all from different zones of time zones in the world. So depending on the time zone, good morning, good afternoon, or good evening to you. And I can see that a few participants are from Spain. So congratulations to them for when going into the final of the soccer cup. I saw that yesterday night, and in fact, I woke up no, no, pretty early in the morning to watch that match. So with that,
Yeah.
so congratulations to that. So with that, let me go through the agenda.
Congratulations.
So I say yes. So what I will discuss is a few fundamental equations, a few fundamental laws of heat transfer, a few modes of heat transfer, and we are all aware of few basic things. We have been studying the heat and energy and thermal engineering, not engineering, the thermal related theory from our school days. So I will touch upon that briefly because that will be the foundation. And based on that theoretical foundation, we will develop and discuss more on the application side, the engineering side of the heat transfer. That is in the when we apply that in terms of uh, enhancing or increasing the heat transfer rates. So that will be in the fins or extended surfaces. I will very briefly touch upon that. And more importantly, I will touch upon the practical or industries where these theories are used. Then we'll talk about the two-phase heat transfer like boilers or condensers, which are traditionally considered to be the areas where we use huge structures and huge machinery or huge equipments for providing energy to our society. And we will also talk about the heat exchangers. Heat exchangers traditionally is one of the most popular and most widely used equipment in all the energy sectors, as well as any factory, any location you see, definitely there will be a heat exchanger. So we'll just briefly touch upon few technical terms as well as the theory and equations, but more importantly, the applications of heat exchangers. Then we will discuss on the third mode of heat transfer. In fact, this is something very pressing for us, that is the radiation, the thermal radiation heat transfer. Radiation can be good, radiation can be bad. So we will discuss on the good aspects of radiation as well as the more pressing and dangerous aspects of thermal radiation and how as in fact, as a responsible human being, how we can contribute uh, to the world, to the planet Earth, how we can contribute in terms of application of our engineering knowledge in this particular area. So I will like to touch upon this, which is in fact very, very serious, serious outcomes of this. Then we will briefly touch upon the mass transfer. Heat and mass transfer are many times combined together, because whenever heat transfers happen in the form of convection mode, mass transfer also accompany them most of the time. And we will touch upon few very recent and important applications of heat and mass transfer in the industry. No matter which industry you go, or you go to the automotive industry, you go to the process industry, you go to the energy sector, uh, then biology, computer, electronics, every area is covered in the heat and mass transfer. In fact, you will be surprised, or maybe some of you may not be too much surprised, but the application is wide range, and that impacts and affects our day in day out life. So that is something which I would like to focus on in a little bit more detail. Then finally, as Marvin has mentioned, you can ask any technical queries or even non-technical queries as well. Marvin will be happy to answer that. Okay, since this is, I would like to make it more as an interactive session. So first question to you, what is heat transfer? So you can just type in your response in the chat box. And what is a basic necessity, or what is a basic requirement for a heat to be transferred? So that is something very, very essential. So what is your understanding in simple layman terms? I'm sure that you must be discussing or studying or learning about heat transfer from your school days. So what is your impression on heat transfer? And we will also look at why actually heat transfer is very, very essential in today's world. Okay, you can type your responses in your chat box. Just a brief about what is heat transfer. Of course, the definition is mentioned in the on the slides, but I would like to hear from you. What is the necessary condition, or what is a basic minimum requirement for a heat to be transferred from one object to the another object? Okay, let me just check. Absolutely correct. Absolutely correct. Temperature gradient or temperature difference. And Sunil also mentioned the energy moves from higher energy state to the lower energy state. So that is something we must be aware, that heat, we know heat is a form of energy which transfers from one object. Object can be a solid, object can be a liquid, object can be a gas. And that energy is transferred from that particular object to another object, but it must obey the laws of thermodynamics. And it is possible only when the temperature difference is maintained and energy always transferred from higher temperature or hot object or hot body to the colder body. And how this energy is transferred, that is known as the modes. So modes can be in solids, it can be a conduction. In liquid, it can be a convection mode of heat transfer. And another mode of heat transfer, which actually does not require any kind of medium, that is the radiation. And thermal radiation, we're specifically talking about thermal radiation heat transfer. So these are the three modes of heat transfer, and all modes of heat transfer involve or require temperature difference. Temperature difference is need to be generated, and always it flows, the energy flows from higher to the lower temperature. Okay, good. So once we know that, let us briefly look at how the different modes of heat transfer work. Conduction happens whenever uh, you know, the heat is transferred in a solid, in a stationary medium. It can be a solid or it can be a stationary fluid. But usually uh, we will have that in solids. And how about convection? Whenever there is a temperature difference between a surface and a moving fluid. So notice the difference here. For a stationary fluid, conduction is the mode of heat transfer, but it's very, very difficult to maintain a stationary fluid. Whenever the fluid is heated, it actually starts moving towards from the higher state to the lower state. So whenever the fluid is moving, there is a different mode of heat transfer that is known as a convection heat transfer. In fact, there are many, many applications in pure conduction mode of heat transfer, and there are plenty of applications in convection mode of heat transfer. And the third mode of heat transfer, which does not require any kind of medium, of course, it can transfer through uh, air, it can transfer through liquid, it can transfer through solids, and it can transfer through gas as well. That is the radiation and thermal radiation. And radiation is nothing but an electromagnetic wave. We're surrounded by electromagnetic waves. Everything is electromagnetic waves. But when we talk about radiation, we're specifically talking about thermal radiation. And thermal radiation is specifically uh, have a certain wavelength or certain band of wavelength within which the thermal radiation happens. So we will focus only on thermal radiation. There are other types of radiation. We will not be focusing on that. And what I'm trying to give you in this particular webinar is a kind of a flavor of all these kind of a fundamental theory and equations and concepts when I teach in the particular unit at the bachelor's level or the master's level. I go deeper and deep dive into an individual topics and discuss more on that. So as I just now discussed, conduction happens in solids or a stationary fluid whenever there is a temperature difference. Let us say T1 temperature is more than the T2 temperature. The energy transfers from left side to the right side. Similarly, convection happens if the surface is hot and the moving fluid is having a lower temperature, then the energy transfers from the surface to the surroundings. And for the radiation, remember every body, whether it's a solid or a liquid or a gas or vapor, everything, every object radiates. And what is the condition, necessary condition for a body to radiate? As long as the temperature of the body is more than absolute 0 degree Kelvin. And you will notice that, yeah, temperature more than 0 degree Kelvin. So practically everything, every object radiates. In fact, right now, our human body, that's radiating. And the laptop which I'm using, the laptop is radiating. The mouse which I'm using, that is radiating. Everything surrounding is uh, radiating. Every object is radiating. So always we need to calculate the net radiation heat exchange between the surfaces. So it's not that only one surface radiates, every surface is radiates. So we need to subtract and addition of this radiation heat exchange we need to do. Um, I won't be talking too much on the calculation part of it, but I will focus on more on the practical application part of it. Now, when we talk about heat transfer, we cannot neglect the laws of heat transfer or fundamental equations. We just need to um, not remember, but understand three important equations, each equation for one mode of heat transfer. For conduction, we have Fourier's law, which talks about um, how much heat is transferred from one higher temperature to the lower temperature in a particular direction, and how much heat is transferred, energy is transferred per unit time, that is known as heat transfer rate, and divide that with the surface area, then we get the heat transfer flux. So flux, the term flux is used for denoting the heat transfer rate per unit area. That's why you will notice the unit here, watt per meter square. And Fourier law says that this equation or this heat transfer flux is proportional to the temperature gradient. I think someone has mentioned the temperature gradient is absolutely necessary for heat to be transferred. So higher is the temperature gradient, higher is the temperature difference, the more is the heat transfer. That's as simple as that. And what is a constant of proportionality? This constant is known as the thermal conductivity, and it's a property of a material. Copper, gold, higher is the cost of material. In fact, more good conductor, or they're pretty good conductors of heat, except diamond. Whereas non-metals are bad conductors of the heat, and we already know that the asbestos or porcelain or refractory bricks, they are pretty bad conductors of heat. So the lower thermal conductivity means they are bad conductors. Higher thermal conductivity means good conductors. Now, can anybody notice here there is a minus sign, right? There is a negative sign here. Why there is a negative sign here? Can anybody answer that? There is a mathematical reason behind this negative symbol or negative sign. Why we provide, or why Fourier's law actually includes this negative or minus sign. Any idea? Okay, yes, very good. It shows their energy flow direction. Yes. Okay, energy is flowing from hot to cold side. That's good. Any mathematical reason why minus or negative sign is, of course, a mathematical symbol? Why we multiply this minus here? Now notice, whenever we see in mathematics, not only heat transfer, in any differential mathematics, whenever we say dt or delta t, typically what we denote is the final value. In this case, it's a temperature, final temperature value minus the initial temperature value. So it's a temperature, but if you say it's a velocity or acceleration or something, some other parameter, the mathematics remain same, always the final value minus the initial value. And here we are saying in the heat transfer that the final temperature is always colder or lesser than the initial temperature. Do you agree with this? Heat transfer can happen only from the initial temperature, which should be higher than the final temperature. So Tf minus Ti, or the delta T value or temperature difference, is always a negative quantity or negative value. But we cannot have a negative heat transfer rate equation or heat transfer rate value. So to make it positive, to make it Q positive, we multiply this with another negative quantity or negative sign to make it a positive number. Okay, I hope that makes sense. So that is why we multiply minus sign, and which must obey the second law of thermodynamics, which says that energy must flow from higher to the lower energy body. Okay, now let us talk about the second equation that is given by the famous scientist Newton. Newton is everywhere. So Newton's law of cooling says that convection heat transfer, suppose we have a surface here, heated surface, hot surface, on over which we have fluid, let us say air is flowing on that. The energy will be transferred from hot surface to the air, and that is provided by this equation, which again says that heat transfer flux or heat transfer rate is proportional to the temperature difference or temperature gradient. And here, the constant of proportionality, we're introducing another term here that is known as the convection heat transfer coefficient. This is valid only for fluids, not for solids. For solids, thermal conductivity K. For fluids, convection heat transfer coefficient H. Higher is the H value, more is the heat transfer. And in many situations, we generally would like to increase the Q value or increase the heat transfer value. In some cases, probably for insulation, we will not like to have higher Q. Now talking about the third mode of heat transfer and third law of heat transfer. Of course, there are many equations. I will be focusing just the fundamental equations. Then I will move on to the application side. The radiation is typically governed by the Boltzmann law. And we're calling the radiation heat transfer as emissive power. As I mentioned, every body which has got more than the absolute 0 degree Kelvin temperature that radiates. And how much is that energy rate of radiation rate? That is proportional to the fourth power of the absolute temperature of that body. So if there is an object having temperature T, then T to the power 4 is the kind of impact the radiation energy will have or emissive power will have. So what it means to try to understand from the application point of view, at lower temperature, perhaps we can neglect radiation heat transfer. But at higher temperature, when I say higher, it typically means 800, 1000 or more than 1000 degrees centigrade, we will have very dominating thermal radiation mode of heat transfer. And that will simply dominate the conduction and convection mode of heat transfer. So that is why you will notice that when we talk about outer space, or when we talk about solar system or sun's energy or kind of like that, we're typically talking about temperatures much beyond 1000 degrees centigrade. And that is where the radiation mode of heat transfer is the most dominating mode of heat transfer. It is possible in real world, all the three modes of heat transfer exist simultaneously. Conduction and convection, interestingly, are available or possible only on Earth. But radiation is possible in outer space. It does not require any kind of medium. All right. Okay. And there we introduce the concept of black body, which is an absolute perfect body to which absorbs all the radiation falling on it. You might have heard of the concept of black hole. No light can escape black hole. So similar kind of concept is used in black body radiation. So I won't be talking too much on this, but these are the few fundamental equations for conduction. Let me just go back. For conduction, Fourier's law. For convection mode of heat transfer, Newton's law of cooling. And for radiation, Stephen Boltzmann law, and as well as the Planck's law of distribution is applied. Now, is it possible to have combined mode of heat transfer? Conduction, convection together, radiation, convection together? Yes, possible. Solids involve conduction and radiation, but not convection. Fluids have got convection and radiation mode of heat transfer, but not conduction. Now, interestingly, one of the key point here is that most gases are transparent to radiation. However, some gas or some certain chemical compound can absorb radiation. And one of the most important example here is the ozone layer. You must be hearing a lot, or you must heard a lot about the ozone layer depletion or reduction in the ozone layer. why this ozone layer is such an important for existence of human being, because it absorbs ultraviolet radiation. And the moment ozone layer is depleting, the radiation is directly falling on us, on human body, which is absolutely harmful for human body. So we will also discuss when we discuss in the units typically the effect of this radiation on on the detrimental side as well as the positive side. Uh, can we say radiation, thermal radiation is possible to be a positive side? Yes, absolutely possible. Radiation we're using for heating a furnace. Radiation is used for heating our home. Radiation is used for microwaves. We use microwaves daily for our cooking, and radiation is the mode of heat transfer which is used in microwave cooking. So radiation has got a positive impact as well, and negative impact as well. All right. Okay, so I'm just checking in case. So the queries or questions you can just post in the chat box, and Marvin will collect those questions, and few of the questions we'll try
Yeah,
to test that.
those questions on
Okay.
the chat so that we can actually answer them. Thank you so much.
Okay, great. Now, see, these are the fundamental equations we have discussed. Now, let us focus on the application side of it. So first application which I would like to discuss, or a general application, is how can we increase the heat transfer? In many cases, we would like to increase the heat transfer. In many examples, we would like to cool a surface. You can take the example of semiconductors, computers, electronics, where we're surrounded by electronics, computers nowadays. Nothing is possible without using them. And one of the key or dangerous aspect of electronics is that it's very, very sensitive to temperature. At higher temperature, nothing works. Our mobile phone won't work beyond certain temperature. Our laptops won't work. Microprocessor won't work. Everything is dead beyond a certain temperature limit. So what to do? We need to remove or dissipate that heat. How can we dissipate the heat? There are two ways of doing it. If you look at the Newton's law of cooling, if you want to increase the heat transfer rate, either we increase the H, which is the convection coefficient, or we can increase the surface area. Remember, in heat transfer, surface area is something which always we try to talk about. We try to always increase the surface area, not the cross-section area. Cross-section area has got very little impact or effect on the heat transfer rate. But higher is the surface area, higher is the surface, more is the heat transfer rate. So we can increase either by increasing H. So how can we increase H? We can use a fan or a blower or a pump. Typically, we need to increase the circulation of fluid so that we can increase H. But many times it's not possible. We have a very space limitation. We cannot put big blowers or fans inside our laptop or devices or electronics. Or so that's why the other option is, can we increase the surface area? Yes, it is possible. So increasing the surface area by attaching some extension which are known as the fins, which looks like our fins of a fish. They are extended surfaces, additional area we are attaching. So how does it look like? It may look like something like this. So you might have seen the transistors, the capacitors or electronic components, the microprocessors. You might have seen a microprocessor, which is a very, very small component. However, on top of that, we actually provide a lot of these extended surfaces, or which are also known as the fins. The primary purpose to increase the surface area, and by increasing the surface area, the heat will be dissipated so that the the electronic component cools down. It is not only for electronic component, it is used for engines, automotive engines, the two-wheeler or four-wheeler or even the bigger engines. Engines also get heated, so we need to dissipate the heat to cool it down. So one of the key application is that we need these fins for uh, dissipating that heat. Earlier, if you look at the area or the job aspects or the career aspects of a mechanical engineer or a thermal engineer, they're pretty much limited to the thermal power plants, steam power plants, steam turbines, or let us say coal plant or a steel industry or something like that. It was never thought that technological based company like let us say Intel or HP or IBM, the computer manufacturer companies or high tech, so-called high tech companies would be looking for mechanical or thermal engineers. However, due to this particular application, there is an absolutely lot of demand for good uh, you know, analyst or good thermal engineers who can actually solve this problem. And this problem is um, it's not completely 100%. It's not yet solved. So there are still a lot of research is going on. Now looking at the various types of fins, we can have pin fins, triangular, rectangular, circumferential, and as the type of the fin changes, the equations and other things changes. I won't be going into the mathematics and equations on that, but things get complicated as we change the cross-section area or the shape of the fins. Now, the first question will rise is that when we are adding fins, we're actually increasing the weight, we're increasing the cost of a product, where we're adding material. And usually these material are copper or aluminum, which are expensive. Copper is definitely expensive. So we're adding cost, we're adding weight, and many cases weight is not good, but like aerospace industries, automotive industries, where or even the electronic component, we don't want heavyweight electronic component or heavy automotive vehicles. So we need to be very careful about adding fins. So fins should be added only when it is effective, only when fins enhance heat transfer. So we need a parameter which is known as the fin effectiveness, which is nothing but simply the ratio between heat transfer rate when we use the fin, divide that. What is the heat transfer rate when we don't use the fin? Are we getting an improvement if the fin effectiveness is more than 1? Yes, good. So in fact, practically it should be as high as possible. It should be more than 3, 4, 5, or 10 times more than without fins. Then we can say, yes, definitely we can go ahead with fins. But it is possible, practical also, it is possible that we may have, after using fins, we may get effectiveness less than 1. Then there is no point in using fins. So fins should be used only when it is necessary and only when the effectiveness is greater than 1 theoretically. Now, how do we design fins? Simple equation. Oh, no, of course, there are many other complication things, but simply fins are good. Good design fins typically means good material fins. And what is a good material? Higher is the thermal conductivity, more is the effectiveness. So that's why we use, we can use gold, we can use silver. They're pretty good thermal conductors, but of course they are very, very expensive. So other materials are copper. Copper is good thermal conductivity. However, copper is also dense. They're a little heavy as well as costly. So we have next best alternative is aluminum. Aluminum is lightweight, easily available everywhere. It's available. The thermal conductivity is also pretty good, and it's very cost friendly as well. So most of the time, uh, designers prefer aluminum as uh, the material for fins. Then we can also try to increase the surface area and reduce the cross-section area. So higher perimeter by reducing the lower cross-section area. So that is something we can do, and it should be used with a smaller edge. Now, one thing you might notice is that fins are not single fin. They are used multiple, like there are tens, 20s, 30, 40, 100, or sometimes it can be 1,000 fins. So we need to calculate the total heat transfer rate. I won't be going into the deeper into the equation, but simply it means that whatever area is not finned plus the whatever area is finned. So we need to consider both, and we add these two and we get the total heat transfer rate. So, when we generally discuss in a specific unit about the fins, so generally we talk about how do we design and how do we calculate all these parameters. The next mode of heat transfer, quickly I will go through, that's the two-phase heat transfer. That's the convection. Two-phase. So what are the phase? We have three phases: solid, liquid, and vapor. So when liquid to vapor changes, phase changes whenever we heat a liquid, it vaporizes or it goes into a steam. It converts water into steam. That's the boiling process. And that's the basic purpose of a boiler. Boiler produces steam. And steam has got a lot of energy, a lot of kinetic energy, which is used for steam turbines, which is used further for generating electricity. So steam power plants, boiler is a very, very fundamental equipment. The reverse of that, when we convert vapor into a liquid, when we cool vapor, we have got evaporators, or we have got the condensers for that. So boiling and evaporation, they are typically liquid to vapor processes, and the reverse of boiling is the condensation. So this is a typical boiling curve. Just one point which I would like to highlight here is that boilers, you might have heard a lot of accidents in boilers. So what is the prime, or what is the fundamental reason why these accidents happen? If you notice this boiling curve, typically when we heat water beyond a certain temperature, beyond, let us say 130 degrees centigrade, beyond this point C, any further, even the slight increase in the heat flux, that will result into a tremendous increase in the temperature. You can see from 30 degrees of excess temperature, it goes to beyond 1000 degrees centigrade. And you know that most of the metals uh, by using which the boilers are made, that will melt, or that will lose its strength, mechanical strength, beyond 1000 degrees centigrade. And that is where the structure failure happens. That's where the blast happens, and then a lot of accidents happen. So the fundamental thing about the boiler is always design your boiler below this critical value of the heat flux. So how to calculate this heat flux, etc. I won't be talking about that in this webinar. Of course, we can discuss that in the course in more detail. Now, condensation, as I mentioned, that's the reverse of the boiling process, vapor to um, liquid. So we can have film condensation or drop-wise condensation. Drop condensation is typically better than film condensation. Now, heat exchanger, again, a traditional and very popular equipment which falls under the convection mode of heat transfer. Simply, we will try to understand. We have two fluids. One is a hot fluid, another is a cold fluid. And they are not mixing with each other. They are flowing through a pipeline, multiple pipelines. If they are flowing in a same direction, they are called as parallel flow heat exchanger. If they are flowing in a different opposite direction, they are known as the counterflow heat exchanger. To simplify this, heat is lost by the hot fluid, and the same heat is gained by the cold fluid. That's why the cold fluid temperature increases, hot fluid temperature decreases. And As a thumb rule or a general idea, counterflow heat exchangers are better than parallel flow heat exchangers. I won't be going into deeper into that, but these are the few fundamental equations which you will need. And this is something maybe some of you may be familiar. This is a shell and tube type heat exchanger, which is very popular, widely used in industry, where we have multiple tubes. So when we say design a heat exchanger, basically what we mean is that how many tubes will be required, what is the diameter of the tube, what is the length of the tube. So when we discuss about heat exchanger or designing a heat exchanger, typically these are the parameters. So what indirectly it means that how do we calculate the surface area? So we need to calculate the surface area. So there are two methods which we can apply. One is the LMTD method, which is log mean temperature difference method. Another is effectiveness NTU method. LMTD method is typically used when we know all the temperatures, both at the inlet as well as outlet. If we know that these temperatures, we can calculate the surface area. If we don't know the temperature, then we use another method, which is known as the effectiveness NTU method. So in this webinar, I'm not going into the mathematical equations on that. Uh, but as a thumb rule, generally we try to calculate the surface area using these two methods. Simpler one is the LMTD method. If you know all the temperatures, then very good. Go ahead with that. But in many practical applications, we don't know the initial temperatures or outlet temperatures. That's why we use effectiveness NTU method. For the time's sake, I will just quickly go through the third mode of heat transfer, then the few applications. Radiation heat transfer, as I mentioned, these are the electromagnetic radiations. Interestingly, all the visible lights, like we can see colors, all the rainbow colors and all, these are all fall under the thermal radiation. Remember, not all the radiations are thermal radiation. For example, gamma rays, X-rays, they are not thermal radiation. Only part of the ultraviolet rays, infrared rays, the visible lights, these are the bandwidth in which we can call that as a thermal radiation. And it can depend on the wavelength, which is known as spectral nature, and it also depends on direction. So radiation is not same in all the directions. It changes if we change the direction. So these are something which generally we discuss in more detail when we talk about radiation heat transfer. And a few more terms on this. Um, Typically, when radiation falls on an object, part of it gets absorbed, part of it gets transmitted, and part of it gets reflected. So these are typically given by these terms: reflectivity, absorptivity, and transmissivity. So I will share all these slides, hopefully, to all the participants. So I will share all these slides, hopefully, to all the participants. So you can go through in more details on that. Then Planck's law of distribution typically talks about how the radiation values changes with the wavelength. And what we notice here typically is that at a certain wavelength, there is a peak or maximum emissive power. And then if you go beyond that wavelength, the emissive power decreases. And if we join all these points together, maximum points, we will notice that as the temperature increases, the wavelength decreases, which is typically known as the Wien's displacement law. Now, what is the practical application of this equation? If we know the temperature, we can calculate the wavelength. And if you know the wavelength, then we can calculate temperature. So you must be wondering how we measure the temperature on sun. How do we measure the temperature of Jupiter or some other star? Generally, what scientists do is that they measure the wavelength. They measure the wavelength, and using this equation, they calculate the temperature. So we cannot put sensors on sun and calculate temperature. This is the indirect way to find out the temperatures of planets and other things, or very distant objects. Very brief about the mass transfer. I would like to touch upon this. Very similar to the heat transfer. Here again, in heat transfer, temperature difference is necessary. In mass transfer, concentration or density difference is necessary. So whenever we have fluids from higher density, it can be fluid, it can be solid as well. From high density to lower density, the component actually fall or flows. Then we can call that as a mass transfer. It can happen in solid, liquid, or vapor. Like some examples, like we can have mix of nitrogen, oxygen. We can have transfer from nitrogen molecules to oxygen and vice versa. So many applications like liquid to gas possible, like evaporation, then solid to gas, solid to liquid, and one of the important engineering application is solid to solid diffusion, which is known as the case hardening. Many applications, we want to just harden the surface of a material, whereas inside of the material, we want it soft. So how do we make it hard? We put more and more carbon on the surface. So how do we diffuse carbon on the surface? Using this process. So diffusion process is a case hardening process, is a metallurgical process. Metal industries, they pretty much use this concept. So you will know that uh, this heat and mass transfer is not limited to a particular industry. It is applicable to, in fact, all the industries. So that is something which I would like to quickly go through. The recent advancements and practical applications. Some applications we have already seen, the traditional applications in boiling or the steam power plants, heat exchangers, fins. Apart from that, any other application? Absolutely. Heat transfer is the fundamental requirement. Knowledge of heat transfer is fundamental requirement for our survival. We know that our body reacts to any kind of sickness. So what is the first indication of that we're not well, we're sick? What is the first indication? Is that our body temperature rises, increases, the fever. So when we say fever, we just measure our temperature. So temperature is a very, very important indicator of our well-being. So it's a difference between sickness and health. And we, of course, we do the radiation part of it, convection, evaporation, conduction, whatever we have discussed, everything is applicable in our biological system. And we have very, very small bandwidth of temperature. So that's why we need to be very, very careful that um, our planet Earth's temperature is actually increasing every year. And beyond certain temperature, human body cannot survive. So we need to maintain or keep that temperature down of our planet Earth. So the knowledge of heat transfer, radiation heat transfer in particular, will be very, very helpful in obtaining the sustainable and other things as well. Other applications in biomedical engineering, particularly laser surgery. Laser is nothing but a thermal rays. Cancer treatment. Absolutely all the technical details of the transient heat conduction is used in cancer treatment. So what generally we do is that we would like to uh, you know remove the tumor. We don't remove the tumor, but we kill the bad cells, bad nanocells. So we put laser light on that, and it absorbs all the incident radiation, and the cells die. Whereas we need to be careful that only at that location, wherever is the affected area, that is the point where the laser need to be focused. Other areas should not get affected. Of course, that's very, very difficult to control, but using the latest equipment, it is possible. And what is the time required? How much time it need to be exposed? How much laser power is necessary? How much is the heat transfer happens? All these are actually used. All the theory which we have discussed just now are being used in this. So it's absolutely, you can say, life and death situation is the application of heat transfer. That is something is latest advancements. Other areas which we have already discussed, the electronic component, it need to be cooled. So microprocessors, computers, everywhere we use fins, heat transfer concepts for dissipating the heat. Manufacturing processes. We have discussed about the laser part of it. Furnaces, all the furnaces uses the heat transfer process. Casting, steel making, metal making, aluminum casting or steel casting, any kind of metal manufacturing process involves heat transfer. Machining, cutting, thermal fluid or cooling a particular machined component or removing the heat, that is also a part of the heat transfer. Friction welding or spot welding, like when we rub two surfaces together, heat is generated and that heat is sufficient to weld them together. That's the friction welding. And infrared sensors, how do we detect a hot object? So motion sensors, automatic door opening, automatic door closing. In fact, a lot of automation can be done using the heat transfer processes. Case hardening or hardening process we have discussed, and electro discharge machining, there's an advanced manufacturing process which typically uses the concept of heat transfer. So what I'm trying to convey here in this webinar is that heat transfer is not limited to a particular area. It's, in fact, if you look at the breadth of applications, it's huge. Next is the energy and engineering systems. Gas turbines typically uses the convection mode of heat transfer to calculate and to design all the gas turbines and reduces the energy losses, etc. And many of these applications are generally taught in more detail or discussed in more detail, depending on whether it's a bachelor's unit or master's, or maybe some of you would be interested in research programs as well, or our doctoral engineering program, where we discuss and actually do good research projects on this topic. Fuel cell, the energy crisis. So we create the fuel cells. That's where also a lot of um, heat transfer concept, which I've discussed, that is being used. Microwave is a very interesting, and day in day out we use it, but probably many of doesn't know that this uses radiation concept for cooking. So it doesn't use convection. For our conventional cooking, we use conduction and convection, whereas for microwave cooking, radiation is used for cooking. Then other heating equipments like boilers, traditional equipments, resistance heaters, water heaters. Oh, no, the application is endless when we talk about heating equipments. Clothing, it's fashion as well, right? It's not just fashion. If you see the astronauts, they actually wear a very shiny and very shiny clothes. Why? Not not just because some designer had done that, because of the radiation. And you might have seen a lot of thermal insulators, sky jacket, which uses the conduction phenomena, insulated phenomena. The body inside the jacket must be hot enough, irrespective of the outside temperature. So it must act like a thermal insulator. Radiation shield is typically astronaut suit, then the firefighter suit, right? All this clothing industry, you can imagine that typically uses a lot of scientific equations, scientific concepts of heat transfer. And I think the final application which I would like to discuss is the electrical components. A lot of electrical components we see. In the previous example, we saw the insulators, or in many areas where we would like to dissipate the heat or remove the heat or capture the heat. That's the insulators. Whereas in electrical components or electronic component, we would like to dissipate the heat. So that is where we use a lot of electrical cables, transformers, resistance heaters, where heat need to be dissipated from these, because heat is a very, very bad element, or temperature is a bad element for electronics, definitely for electrical components as well. And we prevent a lot of catastrophic situations. We might see a lot of cable burning because of heat. So that we can prevent, and we can prevent a lot of accidents and save a lot of human life uh, uh, by using, by understanding the knowledge of heat transfer. So I can just go on and keep on discussing on many, many things, but I think I would stop it here, and list can be endless. So there are some references which I have provided here for your consumption. So I thank you very much for your participation. And yes, I can see some questions. So this is the next
Yep.
will be for the question answer
All right.
session.
Thank you. Thank you, Dr. Vinu. Thank you so much for that very informative presentation. Okay, even I, okay, I was able to understand about heat transfer. Thank you so much for that. Okay, so yep, if you wanted to know more about this one, these are actually the courses that covers the topic. So we have the online Bachelor of Science in Mechanical Engineering, Graduate Certificate in Mechanical Engineering, Graduate Diploma, and Online Masters in Mechanical. Okay. And then, yep, for our upcoming courses, should you wish to study with us, these are the courses that we have. So we have the 13th of August 2024 for professional certificate in mechanical engineering. We also have a professional certificate in fundamentals process, plant layout, and piping design, which is still in August. And then, yep, as you can see on the screen, these are the courses, upcoming courses with intakes. Okay. All right. And then, so, yep, for those who are interested to join us again with our webinars, so these are the schedules. So for this month, we still have our 18th of July 2024 webinar, which is an insight to Bachelor of Science in Industrial Automation Engineering. And then we also have the Industry 4.0 meets Society, okay? The era of digital transformation, okay? All right. So, yep, Doc, before we provide them the QR code and the link for the certificate, let's have a short Q&A. We have some
Yeah.
questions here. Yep.
Yeah, I can read few questions here.
Mhm.
Yeah, Tim is asking about the cooking process. I think I have discussed the conventional cooking, the when we boil water and cook food on our heating equipment or heater. That typically involves conduction. So when we heat the container, the heat transfer through conduction, and from conduction then it moves to the fluid. That is a convection. So it involves the combination of conduction and convection for our traditional cooking. Whereas interestingly, for microwave cooking, it's purely radiation or thermal radiation which is used. I think that answers your question. The mechanism, yes, both the conduction and convection mechanism occur simultaneously, but no radiation. Whereas for microwave, no conduction, no convection, it's purely thermal radiation. Okay, I have got another question for, okay, so we want to design a casing for pumps, inverter electronics, okay. Uh, your fin, I think, if you want to dissipate heat from those your electronic casing is typically an extension of your fins. Instead of making a solid casing, you may try to make it kind of a hollow and uh, kind of make it a more fin or attachment based design. So of course I need to go more deeper into that, but I think that is something will be helpful. So you can look at the various designs of fins. Like triangular fins are available, spherical, it depends on what kind of design you have, the casing design, but you can explore those casing, those fins design. with that. And you need some kind of analysis software. Of course, there are quite a few computational fluid dynamics software which goes along with this. So you can actually simulate and see which design will be more suitable. Okay, let me take the next one. Aluminum in solar panels. Yes. Yes, aluminum, as mentioned. The purpose of the solar panels typically is to concentrate all the heat, and we don't let the heat to be dissipated or to go out. So kind of what we generally do is that we generally try to store that energy within the solar panels. Um, and also this involves a bit of electronics as well as a solar behind all the solar panels or below all the solar panels. A lot of electronics are there, which actually conserves the energy which is generated. So if you are using solar panels for energy purpose, that is a case. Or if you are using solar panels for heating water, then you will see that typically along with the solar panels, there are heating or reservoirs with water filled. That is something attached. So in that case, the heat which is coming from the sun that need to be immediately transferred to the fluid. So the cases are different. If you are using for uh, energy transfer, energy storage, then we need to contain the energy or the heat. But if you want to use it as a water heater, then we need to dissipate the heat or we need to transfer the heat. So application is different, but on the top layer, definitely the solar panels are used. So I hope that answers your question. Yeah, are there any questions? So do you have time for taking any more questions,
Yeah, requesting
Marvin?
everyone
Or
to, yep, if you still
yeah,
have question, we still have few minutes before we wrap up. So basically, as you can see on the screen, this is your link wherein you can actually request for your certificate. However, you need to fill out the survey form first. And for those who want to have topics to be discussed or over the webinar, just kindly fill out the form and we will look into it. All right. So these are the links. I'll be posting as well the link here. Okay, just a sec. Okay, are there any questions? Okay. I think that would be all. Dr. Vino, thank you so much, Doc, for sharing this information with us. It's really insightful and very informative. And even if I don't have any background with this one, but really I understand how he transfers. And yep, thank you so much. Again, thank you for joining us today, guys. We have 100 attendees today. So glad to have that number. Thank you so much. And yep, that's it for today. Have a good one. Have a good one, Doc.
thank you, Marvin, and thank you everyone. So,
Bye bye.
bye bye.